for us. Okay. So how do we optimize this optimization process? Okay. Now, first of all, it's difficult. The main factor here that we need to determine is the learning rate. Okay. How do we set it? At least try a few different values. If you're writing a research paper and you're optimizing your network, try a few different values because it can have a really big influence. Okay. What you can have with your learning rate is if it's too small, it would converge too quickly. For instance, here, very small steps. Oh, I'm stuck here. I can't get out of this optimum. If you have too big steps, it would be unstable. It might jump from here to there, to there, to there, and just have trouble, misses the optimum basically, right? It missed the optimum. So that would make a very diversion. It wouldn't go down slowly. It would go up and down. So if you see your loss function going up and down, try a smaller learning rate. Okay. So our goal is here to find a stable learning rate that converges smoothly and still avoids local optimums, so is big enough to avoid those local optimums. Okay. So first of all, we can try different learning rates, but maybe smarter is we can design an adaptive learning rate that adapts to the optimization landscape. In this case, the learning rate is not a fixed constant, but it can be made smaller or larger depending on how large a gradient is or how fast the learning is happening, maybe the size of particular weights, etc. Okay, so here's this drawing that I just made, illustrated a little bit better. So what happens if your learning rate is too big or if it's too small? Okay. So if we use gradient descent, it works well as we've seen, but there is the matter of this, which it's okay to compute, but it can be very hard to compute over the entire data set because you need to compute it for all of your training set examples, okay, which can be many. Okay. So that means that you might run out of memory if you simply try to put all of those vectors in there. So there's some solution for this problem. Okay. Oh, it's just to summarize what I said. This is a slightly differently formulated version of the optimization function in which they use theta instead of w, but it boils down to the same. Gradient descent, as you see, it's easy to implement, easy to understand, right? It has some disadvantages, so you can be trapped at local minima if your function is not convex, or maybe if it's if your learning rate is not set correctly. Okay, and it requires this large memory because it calculates the gradient on the entire data set. So how do we overcome this? There are a few alternate optimization algorithms that we can use. Now I put the Pytorch code here. So we're actually quite lucky in Pytorch. The only thing we need to do is define our optimizer and all the work gets done for us. All right, so here's one possible solution. Let's initialize the weight randomly like we were doing before. Now we can loop until convergence. Instead of directly calculating the gradient on the dataset, first we pick a single point I. For the single point, compute the gradient. You see a small difference here. J has a little y here. Okay. Now we update the weights based on this particular gradient. Okay. So this is very easy to compute, but it gets very noisy because it's stochastic, right? You're calculating this for one data point. So it's going to be different if you use a different data point. It's not going to be optimized for the same ways. So small variation, which is what in the end we call stochastic gradient descent. Pick a batch of data points. Now compute the same gradient for one data point, but do it for the whole batch. and then average it. Okay. It's still fast to compute, and it's a much better estimate of the true gradient than just taking a look at one data point. Okay. And then again, same thing, we update the weights. That's it. So this is stochastic gradient descent. So it's a variant of gradient descent whereby we use a batch instead of the whole data set. It tries to update the model's parameters much more frequently. So it doesn't go through the entire data set, but it splits the data sets up in batches. So it can actually converge in less time because it updates these parameters quicker. It requires less memory because we only need to store the batch in memory, not the entire data set. And may get to new minimas. Exciting. So some of the disadvantages is there can be a high variance in the model parameter. Okay. So it may shoot up again after achieving a global minimum. Why is that? Because what is the global minimum might be, if we take a particular batch, it might have a different minimum than the global minimum for the data set. Okay, so that's sort of a balance, that it might temporarily go out of the global minimum. So to get the same convergent as the gradient descent, we need to slowly reduce the value of the learning rate. So by using these mini batches, we get a more accurate estimation, smoother conversions, all good things, basically. We can even parallelize the computation. Here's another type of learning algorithm, so optimization algorithm basically, whereby the learning rate is changed dynamically. So mu, or the learning rate, for each parameter is changed at different time steps. It is great that it changes because it can adapt better to the data. It's able to train on sparse data. But it is very computationally expensive as it makes use of the second order derivative. So it's a little bit more math involved. Okay. We won't go into details of Adadelta, but suffice it to say that it's actually learned in a very used in a very famous research paper on the GLOV model, which is an NLP, natural language processing model, and also a famous research paper on recognizing cats from YouTube videos. So it does work. But there are some adaptations to this algorithm, which is, for instance, Adadelta. It's an extension of the original Adagrad, and basically it removes a problem that the original Adagrad algorithm had, which was one of decaying learning. Okay, so its main weakness was that there was an accumulation of the squared gradients in some denominator, which basically caused a decaying learning rate problem. So instead of accumulating all these previously squared gradients, Adadelta limits the window of accumulated past gradient to some fixed size, so it doesn't look back so far, and that actually greatly improves the algorithm. Okay, so now the learning rate does not decay, but it's still computationally very expensive. Atom optimizer, very popular optimizer, adaptive moment estimation. It works with momentums of the first and second order, and the idea is we don't want to roll so fast because we can jump over the minimum. Okay, again, this sort of idea that we could jump back and forward, I don't know, okay, and sort of ignore the actual minimum instead of sort of slowly going towards the minimum. So I'm not going to go into details about how the maths inside these optimizers work, but suffice it to say that the method is very fast and converges rapidly. It doesn't have the decaying gradient problem, but it is still computationally costly. So keep that in mind when you're selecting an optimizer for your problem. Okay. So I found a little graph that compares the different optimizers. What we see here is Adam is typically quite fast. Adagrad seems more slow. Stochastic gradient descent also quite fast. Now take a note that this is for this particular problem, okay, which I took from a Medium site. But it's sort of interesting whenever you would be exploring how well an architecture looks, is to have a look at how quickly the optimization happens and realize that this can be different for different optimizers. See how slow Adadelta is. Okay. All right, that was a lot of math. Let's take a very short break. So what are some of the practical issues that we need to deal with when we are training models? We talked about different types of errors, bias errors, variance errors in the last class. But I want to quickly bring to your attention again that models can be underfitted, so they don't fully learn what's in the data. And they can also be overfitted. When they're too complex, they have too many parameters, too many exponents, coefficients, etc. So meaning they don't work well for new data or they don't generalize well. Two often used remedies. So in addition to some of those that we already mentioned in the previous class, I want to mention these two because specifically in neural networks are very important. One is you might want to, this is for overfitting. One is you might want to reduce the number of features. Now this is an important one. Very often our networks become very heavy on the number of weights that we need to learn. You might say, what? We only saw like 6 weights in the previous example. But if you're looking at some of these deep neural network models, we're talking about 2 million weights they need to update each time a training set is done. Okay, so reduce the number of features can help you overfit. Maybe you also want to try a different model. CNN models, convolutional neural network models, typically have way less weights to learn than normal fully connected models. Maybe you want to manually select which features to keep or do some feature selection in advance. Finally, we also have regularization. So in this case, we keep all the features, but we reduce the magnitude or the size of the feature vector I. How do we do that? Okay, let's have a look at that. So how do we do regularization in neural networks? Okay, so how do we improve generalization of our model for unseen data? There's a few techniques. Dropout, early stopping, stop the training before it overfits to the data, augment your data, add some prior knowledge to a model. Let's look at some of these in more detail. First of all, we can drop some nodes. Okay. What happens or how does that work? We simply put some random nodes in the network, put their weights to 0 so they don't count. So we make our network a little bit sparser. Very easy. In Pytorch, you add a dropout layer. This will drop half of the nodes to 0. Okay. Interesting, and it can actually really improve your overfitting. Stop training before the network overfits. So it's very important, if you remember, to not just look at your training loss, because that's the loss that's standard printed when you train your model. Have a look at your testing loss as well. All right, we can augment our data. If we have more examples that are more robust, we can actually teach the model to become more robust for unseen data as well. And it might sound difficult, how do you create new data? But here's a very simple example. If you have an image, you could rotate the image, you can sort of compress it, you can rotate it upside down, you can add some noise. And if you add all these things to your data set, you make it more robust, meaning that your network will learn how to deal with all of these types of examples. Okay. In a data loader, in Pytorch, it's very easy to add some possible transformations to image. Rotate, flip right to left, flip upside down, add some random noise. It's very easy to add this while you're sampling your data for training. Okay. We can also regularize. So if we regularize, what we do is we sort of do feature selection by assigning a penalty to insignificant input features. Okay. So in our loss function, we add this term, which looks at the coefficients or weights, the absolute value, and depending on your regularization constant, you can penalize more or less. So if your lambda here is 0, then we don't have any regularization and we might be overfitting. If L gets excessively large, then we penalize all weights. Your model becomes super simple with a lot of weights and coefficients dropped, and that means that it's most likely going to be underfitting. Okay. Second type of regularization, slow, it's just a very variation basically of the previous L1 loss. It's rich regularization. It forces the weights to be small, but it does not make them 0. So this causes non-sparse solutions. So by taking the power of the coefficients to the power of 2, okay, it forces them to be small. Again, we have a regularization term. Okay, so how do we implement this in Pytorch? Okay, so L2 regularization is actually included in some optimizers. For instance, in Atom Optimizer, you can just put your regularization constant here, or you could do this manually. You define your regularization constants. Here we use stochastic gradient descent optimizer. We reset our gradients, so we sort of reset the training. We do a forward pass to get the outputs based on the model given some inputs. We calculate cross-entropy loss. So to calculate loss, we need the predicted, y hat and the target y, the real labels. Then we retrieve all the parameters from the model, from layer 1 and from layer 2. And if we do L1 regularization, then we can call the norm function, multiply it by lambda 1 for layer 1, and we can call the norm function for layer 2 in case of L2 norm, we need to put a 2 here and multiply that by lambda 2. Okay, so our final loss will then be our cross-entropy loss plus each regularization term that we want to add. We do backpropagation and update our weights. So another great regularization method is batch norm. Okay. Batch norm comes from a paper in 2015. It allows faster training, improves regularization, reduces dependence on initialization of the weights. So sometimes a random initialization of the weights is not the way to go. It improves accuracy. And how is this done? Basically by ensuring that for each batch, the items or the instances are standardized with mean 0 and standard deviation of 1. Okay, so then we shift and scale the training instances. And what's interesting here is that the network during training can actually optimize this gamma and beta coefficient. All right. So this one is trainable. Using batch norm gives us a lot of benefits. Okay. So let's have a look at other network topologies. There are many different types of networks. Click this link and you can scroll down a little bit more. So we have the original perceptron from which we started. We expanded this to feed-forward neural networks, deep neural networks. Now we're going to very briefly look into RNN, LSTM, autoencoder later on in the last week of classes. Let's see what else we have. Denoising autoencoder, variational autoencoder, convolutional networks. And I think some may be further down the page. But this is actually very cool. If you know a little bit about machine learning already, go to this network, this web page, and have a look at which networks you're familiar with or not. First of all, if we're doing sequence modeling, So for instance, given an image of a ball, where will it roll to? If we have stock market prediction, given all the previous stock market movements, where is it going to go now? Okay. We need to be able to model our sequences. And to do that, we're going to be using something called recurrent neural networks, but we're going to be looking at that in a little bit. Other examples of sequence input or sequence data are sentences. This morning I took my cat for a walk. So given a sentence, how can we represent text? And I'm going to be talking to you very briefly about word vectors, which is or word embeddings, which is a very popular technique in NLP these days. Okay. There's some traditional ways of representing text, such as bag of words, BOW. In bag of words, we just have a column for each of the words in the dictionary, and we put a 1 when they occur or a 0 when they don't occur. So in this case, we're representing our first sentence, I went to the movies yesterday. Okay. If I have a sentence, I went swimming, then it would be I went swimming. Okay. Something that is immediately apparent here is that what there are 20,000 words or something in the English language to represent I went swimming, I need 20,000, almost 20,000 zeros and 3 ones. So it's a very, very sparse representation. This is going to become a problem when we're learning models. A related but slightly more improved representation of text is TF-IDF, term frequency inverse document frequency. So this one focuses on the fact that rare words carry more meaning. So for instance, words like and are going to be having a very low value and others are going to be higher. How do we calculate this term frequency IDF? First of all, we have the term frequency, which is the number of times the term appears in the document, divided by the total number of words in the document. Okay. Then we have inverse document frequency, is the logarithm of the number of documents divided by the number of documents that the term appears in. Okay. Then we just multiply these two terms. Okay. So as I mentioned, so we're not going to go into detail of this. In my data science class, we talk more about this. I'm sure in the NLP class and maybe even the deep learning class, this will be explained in detail. But suffice it to say for now that these are very sparse representations. Very long vectors to represent a sentence, many, many zeros that we really don't need. So it's much more computationally better to look at less sparse model or dense modules, such as co-occurrence models. One such model is SVD, single value decomposition. I'm not going to go into detail in that, but I will focus on vector embedding models. Okay. Two famous ones, GloVe and Word2Vec. We will focus on the latter. So word vectors are all based on something called the distributional semantics hypothesis. This means, or this is defined as, you shall know a word by the company it keeps. John Rupert Firth made this hypothesis in 1957. What does it mean? Words that occur in a similar context tend to have a similar meaning. I enjoyed eating pizza at the restaurant. Okay, so pizza is a word and all that surrounds it is the company it keeps. I enjoyed eating pizza at the restaurant. I enjoyed eating pineapple at the restaurant. Because both of these words appear at the exact same context, we can assume that they share a similar meaning. And it's sort of true, they're both foods that can be eaten in a restaurant. Okay. So based on that principle, we can do unsupervised learning of word representations. So for each word, our goal is to get a vector of coordinates in a multidimensional space that is not 20,000 of size 20,000. Okay, typically word vectors are going to be like 128 or 256 positions long. So much more dense and sparse. A cool thing about these word vectors is if we project them into 2 dimensions, something we can do using TSNE, and something we don't really have the time to go into right now. TSNE is a technique that you can use to project 3 and higher dimensional graphs into 2 dimensions. We can see some very cool things about these representations. So each word has a coordinate and hence a position in space. We see that these learned or these trained models have properties. In a very famous word-to-vec model from Google, they saw that if they do a translation, so a shift in space, of the exact same size from man to woman as from king to, then we see that we end up at queen. Isn't that interesting? That means that that translation with that angle and size equals a translation from male to female. Okay, we see similar translations to conjugate verbs, for instance. So these learned vector embeddings are actually extremely useful for representing words in a meaningful way, because the closer the words are, the more similar they are, and also we can define relationship between different words. Okay. Now, I mentioned there are some traditional methods like bag of words. If we compare these to word embeddings, we see that typically word embeddings are a lot smaller. They can be trained using a big text data set. And the resulting vector looks something like this. So it's not a bunch of zeros and one, it's a dense vector. It is not sparse. All right. So how do we train this model, or how do we get to these word embeddings? Typically, if we look at word2vec, there's 2 different architectures that are often used. In the first architecture, continuous bag of words, we have our input words, this is our sentence, and we project it into a 1-layer neural network that predicts the output. This is our word pizza, and this is the context in which pizza occurs. So we're teaching the network to predict a word given its context. In the second architecture, skipgram, we do exactly the opposite. So we give the model pizza and we learn to predict the context. Okay. Both of these models boil down to pretty much the same thing. All right, so we predict surrounding words for every word. Our training objective here, for instance, would be, I predict what is the chances of the word I appearing given that the context or surrounding word is pizza. What is the chances of enjoyed occurring given pizza? What are the chances of restaurant occurring given pizza? These are the sort of probabilities that you're learning. Okay. All right, so it is trained. Here we look at the skipgram architecture. We give it the input vector. This is a traditional bag of words whereby we have the one word. There's one hidden layer, and we classify all of the output surrounding words, okay, the probability. Now what's interesting here is after we fit this model, after we train it, what we're interested in is this hidden layer. Okay. So it's actually a very quick and very simple model to learn. It's one layer. To train it, we use cross entropy. However, it's quite hard to compute. Okay, so because this loss function is hard to calculate, we approximate it and we do negative sampling. So what does that mean? We take words that appear in the same context. Those would be our positive samples. And we take words that don't appear in the same context. For instance, cat and glass. Then we feed those newly learned representations by the model to a binary logistic regression model, And if this model can easily classify, that means most likely that their representations are very similar or dissimilar, which is exactly what we want from this word-to-vec model. So this is a way to very quickly approximate the training objective. Okay. So the resulting model, the resulting word-to-vec model, is fast and accurate to predict. You can optimize the loss function very well. It captures semantic content, so it captures meaning. It will capture both that pineapple and pizza are food, okay, without requiring any labels that say that pineapple or pizza are food. It's very popular. There's lots of pre-trained models available. That means somebody who's already applied a data set, a training data set to it and optimized the weights. And you can use these weights for different problems. Okay. It is super fast to train, and it's very easy to use in Python. So before we actually look at the Python implementation, how do we actually get these word embeddings? Because fine, we calculate or we get a neural network here. What we are interested in, it's not the output layer. What we are interested in is the hidden layer, which is the latent representation of these words. Now, if we go back to where we were, the hidden layer here, basically this weight matrix becomes our word vector lookup table. We use the hidden layer, I repeat, not the output layer, and we use this latent representation. This is what we call a representation in the middle of a network, a latent representation, as our new word vectors. Okay. All right, so in Python, we can easily, the most easy way is to use something like GenSim. In GenSim is a library that will just allow you to load word-to-vec, load word-to-vec vectors that are pre-trained from a particular model. Okay. Usually you can load the model. For instance, Google has a bunch of pre-trained vectors for a Google News. And you can just load these in a vector and then retrieve the actual word embeddings, which equates to having a word vector for each word. There's other ways to do this, of course, even within Pytorch, as we'll see in the lab. I remember when I did the first research paper on using word2vec, it was like pages of code in TensorFlow just to train a simple word embedding model. So luckily, a lot has changed in this area. Okay. All right, so back to sequence modeling. So we were talking about audio, time series, text, all being sequences that need to be modeled. We have a special type of model for this, because if we were to just feed words one by one into a neural network, we would lose any information about the previous word. For instance, we want to predict this here. France is where I grew up, but I now live in Boston. I speak fluent. Okay. So if we look back, let's say 2 words, from that you can derive that you need to fill in a language here. English, German, Dutch. Okay. We actually need to look back quite far to the beginning of the sentence to derive that we might fill in English or French. Okay. Now, bag of words don't preserve order. Okay. Even word2vec embeddings don't preserve the order of the sentences. Okay, all right, if we're training this, we feed it the window. So we try to predict this word given the surrounding training windows. But if we're actually going to do word prediction, we are not in a normal fully connected neural network. We don't look back. Okay, so we need a special type of model that allows us to assign weights to how far we look back. And this is what we call recurrent neural networks. All right. Recurrent neural networks take variable length sequences. They try to learn long-term dependencies and they maintain info about the order. Okay. What's interesting is that they share their weight parameters across the sequence. Okay. They're typically depicted like this. So instead of just having the neural network arrow here, we have this recurring connection, let's say, that gives the module a sort of memory. Okay, so it can remember the past sequences. Okay. All right, so here we have a one-to-one vanilla or a very simple neural network, okay, where we have one input and we predict one output. Okay. A different type of network would be many-to-one, whereby we have many inputs and we want to predict one output. Interesting here, if we use RNNs, is that there is a connection here, this memory connection, that allows us to look back to the previous word in a sentence, for instance. This is very useful. For instance, if you're doing sentiment classification, you have a whole sentence you want to input here, and you want to predict, is it positive or negative? Finally, we have an end-to-end model, many-to-many, whereby you have a sentence as input and you want to predict another sentence. Think of translations, music generation. You have one bar of music and you want to predict the next bar of music. Okay. There's many variant architectures here that are useful for different types of applications. So if we look at a recurrent cell, it's usually depicted by this sort of recurrent arrow, which will be expanded in the next slide. But it's noticeable that each cell has an HT, which is a hidden state at time t. This hidden state is updated at each time with a simple neural network operation, same as we are used to. We have a nonlinear activation hyperbolic tangent here, and we have a weight matrix multiplied by variables. In this case, there are two types of variables. We have our regular input variables, but we also have the previous time step hidden states. So in this case, that means that our weight matrix is split up in two parts as well. Finally, we calculate the output factor of the neural network by yet another neural network, weight matrix multiplied by the final hidden state, which we just calculated using this equation. Okay. Right, so as I mentioned, this recurrent neural network has a sort of recurring error. This is usually just done for clarity. If you write out the neural network in full, we'll see that we actually can unfold it through time. For each time, we have an input x0, x1, x2, etc. We have weight matrices that we multiply the x inputs with at each time. Note that all these weight matrices are the same over time. This is very important. Then we have a weight matrix that we use to multiply the hidden states with. So in the previous equation, these are this and this matrix. And then finally, we have a third weight matrix to get the final output of the cell. Note that these are the same. These weight matrices are the same, and these are also the same. This is important. Okay, so finally, from the output predictions for each time step, we can calculate a loss function at each time step, and the sum of all loss functions forms the total loss L. In Pytorch, whenever we want to include a recurrent neural network layer, we can just use this RNN command when we're defining our network. Interesting here is that we also need to specify the hidden size. So when we calculate the predictions, we do a forward pass. So the black lines here, these arrows that go forward, starting from x all the way to L. This is to calculate the predicted output. As you know, when we're training a neural network, we don't just do a forward pass. After that, we do a backward pass to get the gradients and adjust the weight. That is the red arrows in this drawing. But in RNN, the forward pass also includes going through time, right? So the errors are backpropagated at each individual time steps and finally across all time steps. That means that backpropagation through time is being executed, which is a special technique, and it is quite hard to do. One problem that we see at RNNs is the problem of vanishing gradients. Okay, so we see again here the forward propagation of the hidden weights, the black line, and then the back propagation the other way around. Okay. Now computing these gradients, sorry, with regards to the hidden, the hidden state 0, the first time step involves many factors of this weight matrix. Remember, it's always the same, plus repeated gradient computation. Okay. This can be problematic for two reasons. Okay, first, if any of these values involved in the repeated calculation, such as either the weights or the gradient themselves, become bigger than 1, then we can have the problem of exploding gradients. Okay, in this case, we can perform gradient clipping to just scale down the big gradients. A more important problem is if these values, either the weights or the gradients, are smaller than 1, then we get a vanishing gradient problem. So you can sort of imagine if a value is small, you multiply it by another small value, and yet again, and maybe over a few time steps. In the end, you'll get something that is immensely small. Okay, and this can happen very quickly. Okay, so it can sort of be an explosive reaction. So there's 3 ways in which we can adapt this, and we'll just go over all 3. First would be through the use of special activation functions. Secondly, by initializing the weights of the network differently. And thirdly, by making some changes to the network architecture, more specifically the type of RNN cells. Okay. So why are these vanishing gradients a problem? As I said before, if we multiply a lot of small numbers together, we actually propagate this error back in the past. It's harder to propagate these errors back in the past because we'll end up blasting our network, so biasing our network to capture more short-term dependence. Okay, so basically the network is forgetting the longer-term errors. This can be a problem. If you remember the sentence, I grew up in France, I lived in some other place sometime, and I speak fluent X. If we're predicting the X here, we need to look back really far to France. And if we have a vanishing gradient problem, then we will not remember the old states very well. Okay. Right. So it biases your network to learn more short-term dependencies instead of long-term dependencies. So the first trick we can apply is to use a different type of activation function. Okay. If we use a hyperbolic tangent or sigmoid activation, the derivative is actually smaller than 1. But if we were to use ReLU, if you remember, if x is greater than 1, it just becomes 1. The derivative is 1 whenever x is bigger than 0. Okay, so this would help prevent our shrinking gradients. Okay, but only when x is bigger than 0, mind you. It's quite important. Second trick, initialize the parameters of the network. Usually we do random initialization, but there's actually better ways to optimize if you're dealing with vanishing gradients. Okay. Apparently, if you initialize to an identity matrix, remember what that is, like the picture here, we have ones on the main diagonal and zeros otherwise. This will help the weights prevent from shrinking to zero. Thirdly, there is a different type of RNN cells, those that have gates. So they're a little bit more complex, but they help control which information is passed through. So for instance, long short-term memory networks, you have also gated recurrent units, GRU. They're very popular types of RNN cells because they're able to use gates to control, forget, update information through many time steps. Right, so if we have an RNN cell, simple computation mode, as you know, we have our input xt, we have our output xt, and we always pass along the previous hidden state, apply the hyperbolic tangents, neural network computation, and get the next hidden state. So if we look at a variation of this single RNN cell, we can look at LSTM cells. LSTM. So these are computational blocks that control the information flow. I'm not going to be going into details on the mathematics of the LSTM cell, but I want you to understand the concept, okay, of how they have an ability to track information over many time steps. If you're using Pytorch, the only thing that changes is here you define LSTM instead of RNN when you make your model definition. All right, so LSTMs have 4 kinds of gates. So they do 4 types of actions. They forget information, they store information, they update, and they output the results. Okay. So first it decides which information to remove from its state, okay, through the forget gate. So all of these gates, they're represented as a sigma sign. This is because they're basically sigmoid activation functions based on a linear combination of weights again. So simple neural network operation with sigmoid activation. So in a forget gate, you take as input the xt, so the inputs, and your previous hidden state. It calculates how much of the information is going to be forgotten or retained, 0 or 1. Or any number between 0 or 1. Then we have the store gate. Store gate takes the same inputs, the xt's and the hidden states of the previous time. And this is a little bit more complicated. It has, like previously, the hyperbolic tangent to sort of our memory, to calculate our memory. Again, pointwise multiplication with an activation function. And it also has a sigmoid function here, which basically will tell the this hidden cell state what to remember. Okay, that brings us to the cell state. So as you noticed, there's not only hidden state that flows to the cell, but we have a cell state. The cell state forgets whatever is the forget gate tells it here. Remember how we calculate this in the forget gate? It adds whatever the store gate tells it, and hence it predicts the new cell state. Okay. So basically using this formula, just adds the two. All right. Finally, we have the output gate. The output gate, again, takes in the previously hidden state and the xt's, does a sigmoid activation, and calculates the hyperbolic tangent of the pointwise multiplication. So this output gate controls what information will be the next hidden state and will be sent to the next cell. Okay. Right, so one of the advantages of the LSTM cell is that the internal cell state, so the C, causes an uninterrupted gradient flow, which means that typically LSTMs won't have the vanishing gradient problem so much. That's amazing, okay? Because the information can just flow back straight through the cell state. Okay. Right, so there's some other types of RNN cells, GRUs, so they have a sort of peephole connection, so they can always look back at other cell states. Another very popular algorithm these days, and it's not an RNN algorithm, is an attention mechanism, attention network transformer networks. You might have heard of models like BERT, very effective models that they look a little bit like an LSTM in functioning, but they're programmed quite differently. They're very good at doing translation tasks. So for instance, in the picture below, we have an English sentence translated into French. Each word of this sentence, at each time, suppose we're predicting zone. In this case, the attention network will look at which surrounding word to focus on. Okay, so it will learn the weight of these connections. Okay, so this is something that we sort of automatically do when we're listening. Some words stand out more, and this is exactly what the network is trying to learn. It's quite effective, and it works on a multitude of problems as well, but it's very recent, like only the last 2 years. So in this week's lab, we'll be putting everything together in Pytorch. We'll make a simple neural network. For those of you daring, we'll do an RNN for a task of sentiment prediction. That means sort of a combination, because we will have a word, a sentence actually of multiple words, which need to be put into their word-to-vec notation, which will then each be fed into an LSTM network to output one sentiment value. We'll check out how to program batches, regularization, dropout, batch norm, all these things that we discussed in this week's lab. All right, so remember, if you have any questions, please visit the forum and ask me any silly question about the class, about teaching. We can discuss anything there. And I'll see you on the Zoom session on Friday.